Hello everyone. This is gonna be a lecture on waveguides, and it's gonna be the first lecture of the series of lectures on signal and power integrity. And the main idea of this particular presentation is to teach you the basics of from electromagnetics, the concept of what a waveguide is, and the behavior of a waveguide versus frequency, and also understand how to go from the design from the concept of a waveguide to the concept of a transmission line. So let's begin this presentation. So first, I just want to recap a little bit. Just give me a second. Yes. Okay. So to recap a little bit, we had discussed the Maxwell's equations in lecture 0, which state that the divergence of the electric field is charge density, the curl of the electric field is proportion is negative rate of change of magnetic flux density. The divergence of the magnetic field is zero because the magnetic field usually has is usually a field that curls around a point. And the curl of the magnetic field has two components caused by the conduction current and the displacement current. So I'm not really going to explaining this further because it was discussed in lecture 0. So now let's talk about the idea of what exactly a waveguide is. So what is a waveguide? So the best way to think to kind of visualize how a waveguide actually works is to consider the following situation. Imagine you had a tub of water and you're throwing a stone into the tub of water. So what happens? So the S denotes the place where the stone was thrown. And when the stone is thrown into the water, it displaces some amount of the water, which excites a wave on the surface of the water that propagates, as shown here, radially outwards. And if I had a piece of paper located at some distance L from the source, I would see that this paper would basically oscillate up and down. And the height, if you plot the height as a function of time of this paper going up and down, you find that the height is going to be the peak value of that height, or the maximum height that goes up or down is going to be proportional to the PS, is the power at the source, which is basically energy with which you throw the stone at the source side, but it falls as 1 over the square of the distance from the source. And the reason why it falls as 1 over L square is because you can see that the energy produced by the energy of the stone, which was transferred to the surface of the water, is propagating radially outwards. So it's kind of getting diluted because it's distributing in a circle. And so at a certain distance away, a small solid angle or a small cone of the original power reaches the paper. So therefore it falls as 1 over L square. So if you want to find a way as to how to increase this oscillations of this paper, what can we do? So one obvious way is to construct a wall. So if you construct a wall like this in the water, then what happens is when we throw the stone, the spherical waves which are produced, the circular waves which are produced on the surface of the water tend to reflect from this wall. And you can see here that the spherical waves go and the circular waves go out and then they reflect and they go reflect again and again and again. And what happens is they keep getting reflected. And you see that the power is now confined to within this wall region, and it's basically propagating in the if you consider this horizontal direction as z direction, it's propagating in the z direction. So if you find out what is the oscillations of the paper, if you find out the height as a function of time, you find that in this case it's just proportional to the power at the source, but it loses that 1 over L square behavior now. The reason is because now the energy is now confined to within this region, so the energy is not allowed to simply dissipate circularly outward. Okay, and this is basically the concept of a waveguide. So what does a waveguide do? A waveguide basically guides the energy from the source to a certain target location or the load by using this kind of structure that essentially keeps reflecting the waves within the structure or confining the waves within the structure, thus allowing it to propagate along a certain direction, in this case, the horizontal direction. This is, of course, not the only way this waveguide would work. There's a second way it can work. The second way is rather than having a wall, you can also have a material, another liquid, having a lower viscosity than water. So, for example, here the middle section is made of water, but the upper and lower sections are, say, alcohol, and say there's a continuous flow of alcohol. In this case, when you throw the stone into the water, the circular waves that are produced, some amount of them would basically escape into the alcohol, but you will find that amount of them does reflect from the alcohol water interface and would reflect back into the water region. And this reflection will take place again and again, so that some amount of the energy of the source is now guided in this basically alcohol water waveguide to the paper. So in this case, if you find out what the height that paper goes up and down would be, the height would be proportional to PS, but it will have a certain it will be multiplied by a certain factor K, where K basically represents how much of the cone of the original propagating energy gets captured within this waveguide. So what that means is there's a certain acceptance cone that's shown here, and as long as the waves are propagating within this cone, they would be reflected at the interface and propagate within this water waveguide. But if they exceed this cone, they will actually end up going to the alcohol. So this K factor is just going to be proportional to the sine square of this angle. And you can see why it has to be that, because if the angle was zero, then in that situation, this value would be zero. So there would be no power transmitted to the paper. But if it was 90-degree, then it would be similar to the case where there's a wall, and therefore it would just be proportional to PS. So now we see that there are two ways of guiding the waves. One is to use a wall, and the other one is to use a material or a liquid having a lower viscosity than the viscosity of water. This analogy applies directly to electromagnetism, because there also you have a wave phenomena. And therefore, in an analogous sense, you have different kinds of ways of guiding an electromagnetic wave through an electromagnetic waveguide. So, for example, the optic fiber would be similar to the water alcohol case. You have one material here which has a higher dielectric constant than the outer material, which has a lower dielectric constant. And in this case, the electromagnetic waves would be propagated along the length of this so-called optical fiber. And here there will typically also be an acceptance angle for accepting the incoming wave into this, for accepting the incoming signal into this waveguide. Because if it exceeds that acceptance angle, then it would end up just leaking away from the core of the fiber. And here you can also have the next three cases actually are waveguides using a metal, and this is similar to the wall case. So here you have a two-wire waveguide there, where there could be basically a signal line here sending the signal, and then a ground line or a return line here, and the electromagnetic field is basically confined between these two wires. Then you also have a coax cable, which is basically an outside metal shell and an inside metal core, and the field is confined within this region that has a dielectric constant epsilon. And finally, one of the most important waveguides we'll be talking about a little bit more is the microstrip. And in the microstrip, you have basically a metal in the bottom, which acts as the ground, and you have this metal at the top, and between them there is basically a rectangular region of dielectric constant, and the field will be confined within this region between the signal conductor and the ground conductor, and will propagate along the z direction. So now that we talked about the concept of what a waveguide is, how an electromagnetic waveguide looks like, let us now go into understand how to analyze the waveguide from first principles, right? So, and we're going to make this analysis in a very general way, so that we are not really restricted by what kind of waveguide we are particularly talking about. So let's consider, but nevertheless, as we have seen, a waveguide is basically something that has some variation in the dielectric constant, metals, and so on in the cross section, but along the direction of propagation of the wave, it has no variation in the cross section. That is, it is uniform along the direction of propagation. So this is typically what a general waveguide would look like. In the cross section, say X and Y denote the coordinates in the cross section, and Z denotes the propagation direction. Then along the XY, basically in the cross section, you could have, for example, three regions with different epsilon 1, 2, and 3. And outside, you can have an epsilon 4. You can also have some metals here, which are shown by this cross-hatched, this cross-hatched region. And then along the propagation direction, it's just uniform. So it's like a little tube that's going along the z direction. So now we need to solve the Maxwell's equations in this system. And these are the Maxwell's equations we have talked about earlier. Now, how do you solve something like this? In order to solve something like this in such a complex region, what we can do is, if you look at the Maxwell's equations, they have a very unique property. That is, the Maxwell's equations have a linear, especially when you are talking about waveguiding phenomena, they actually have a linear, they are a bunch of linear differential equations. And therefore, you can solve, rather than solving the entire system, you can break up the system into a bunch of pieces, solve them separately, and then put them together by using boundary conditions. So what I mean by that is this whole waveguide over here is consists of a bunch of sections. So there could be only this section. This is basically, there's no metal here. It's just showing that it's hollow. So it could just be the epsilon 1 region or the epsilon 2 region, epsilon 3 region, and then the epsilon 4 is just the surrounding material plus just having the metal. So the entire waveguide can be broken into a bunch of these regions of uniform epsilon. And then you can solve the Maxwell's equations separately in each one of these regions to get the E1, H1, E2, H2, and so on in each region, which are the fields. And obviously, the electric field inside the metal is zero. And then once you have solved these basically solved the electromagnetic fields in these regions separately, they can be put together by satisfying certain boundary conditions in the cross section. For example, if you had a boundary with two dielectric materials, epsilon 1 and epsilon 2, there's a certain rule that says how the normal component and the tangential component of the electric and the magnetic field behave across that interface. So by using those boundary conditions and making sure that these different solutions satisfy those boundary conditions, you can get the full general solution for the waveguide in question. And that's basically what I'm describing here. So so now that we know we can divide this entire solution into a bunch of separate regions, let's talk about one particular region. There's one particular constant epsilon region. In this region, obviously, because it's a constant epsilon region, there is no free charge, and also there is no conduction current in this region. So, and also because gradient of epsilon is zero, which is just saying that this material is a uniform homogeneous isotropic material with a uniform dielectric constant epsilon and permeability mu, then the Maxwell's equations, which were described previously, just simplify to this. So del dot E now becomes zero because the free charge density inside this constant epsilon region is zero. And the divergence of the H field obviously is already zero. The curl of the E field is going to be minus mu dH dt. And so what I've basically done here is I replace B by mu times H and D by epsilon E. And these things have been taken outside this differential. So now, once you have these four equations, it turns out that these four equations are not separate equations and they can actually be combined. So the del cross E and the del dot E can be combined by taking the curl of del cross E. So if you take the curl of E, then if you look at any vector calculus book, the curl of E is just the gradient of divergence of E minus the Laplacian of E. And because the divergence of E is zero, you have basically yeah. So because the divergence of E is zero, so yeah, basically the negative Laplacian of E is just going to be minus mu times the rate of change of basically the curl of H. Because remember, you're taking a curl on the left side, so there's a curl of H. And the curl of H we already know is this expression. So if we substitute that here, we get the Laplacian of E is going to be mu, right, d dt of, and I've substituted the value of curl of H, and you get mu epsilon d square E over dt square. So we get an equation which says that del square E minus mu epsilon d square E by dt square is zero. And if you do a similar calculation for the magnetic field intensity, you'll get a very similar equation. Now, these equations have this form. These are hyperbolic differential equations. They have the form that they have a second order differential in space as well as a second order differential with time with a negative sign for the time component. And mathematically, such a differential equation has the so-called wave solutions. So wave solutions are solutions that essentially propagate at a certain velocity in the medium. And these equations have such a solution of the electric and magnetic fields. Also, if you notice, these are completely linear equations. And therefore, if there are two separate solutions, for example, E1 and E2, two different electric fields that are solutions of the electric field wave equation, then another solution, which is alpha times E1 plus beta times E2, where alpha and beta could be some numbers, is also a solution to this equation. So what does this imply? So generally, when an equation has a linear form and you can write the solution as a sum of some eigensolutions to the equation. You can always use Fourier components to analyze this. So now imagine that we have the electric field in this region, which is a function of x, y, z, t. It can now be written as the electric field as a function of x, y, z, with a time harmonic component, which is e power j omega t. So basically what I'm doing here is, because this is a linear equation, I can only consider one frequency component of the time variation, and then to get the general solution, I can just add all the possible different frequency components together to get the general solution. And this would still be a solution of the Maxwell's equations because of the linearity of the differential equation. So you can write the E as E of xyz and times the time harmonic, and similarly H can be written in the same form. And now what you can do is you can substitute this in the wave equation for the electric field. And if you do that and solve this, you get this expression, which is basically the time harmonic version of the electric wave equation. And similarly, you get the time harmonic analog of the magnetic field intensity wave equation. So now let us consider again one of the sections, basically the waveguide in question, the part of the waveguide in question, which is this region with a constant epsilon. We need to essentially solve this differential equation, which is del square E, but only with a space dependence, plus omega square mu epsilon, E is 0 in this region. And now, if you notice something interesting, because of the fact that this is a waveguide and it has no variation in the cross section along the propagation direction z, if you say you're passing a signal through this, obviously the signal, if this is, for example, a lossless waveguide, obviously the signal strength cannot fluctuate versus the propagation direction, right? Because you don't have any variations in the geometry along the z direction, and therefore it is obvious that the intensity of the field cannot vary with z. It must be uniform with z. And therefore, mathematically, we can say that the intensity, the mod square of the electric field, xyz, should be equal to the mod square of the electric field at any other xy, but z plus delta z, where delta z is any number from 0 to infinity, which is just saying that the intensity of the field should not vary anywhere along z. And the only form of the electric field that satisfies this equation for every delta z, for delta z going from 0 to infinity, is when E can be written as E of xy times a phase factor, E power plus minus j beta z. So you can show mathematically that only when the electric field xyz has this functional form for the variation along z is this condition hold for every delta z between 0 and infinity, right? So therefore, what you can see is the electric field in space is going to be just a field along the cross section times a exponential that tells you how the field is basically propagating. So for example, and this is basically adding a phase to the field as it is traveling along the propagation direction. Beta here is a complex number, and beta here is a number and it's typically called the propagation constant. If the waveguide also has loss, then rather than having plus minus j beta z, you would have plus minus gamma z, where gamma will be a complex number, where the real part will denote the decrease in the intensity of the field as it propagates along the z direction, and beta denotes the phase factor or the propagation constant along the z direction. So now it can be either e power plus j beta z or minus j beta z. If it is e power plus j beta z, it indicates a wave traveling along the minus z direction, and if it's minus j beta z, it's a wave traveling along the plus z direction. Why is this the case? It's obvious because if we say we add the time component, so we remember we are considering the Fourier component, and the electric field in space is multiplied by this e power j omega t to add the time dependence. And so if we add the time harmonic component e power j omega t, then the overall phase factor as the wave propagates along the z direction is going to be e power j beta z plus omega t if we assume the plus case, which indicates a wavefront traveling along the minus z direction, while if you have the minus beta z, it is a wavefront traveling in the plus z direction. So we can see how the e power plus j beta z is a wave traveling along the minus z direction, while e power minus j beta z indicates a wave that is traveling along the plus z direction. Now for simplicity, let's consider that the wave is only traveling on the plus z direction, and therefore the electric field in space, which is E of xyz, can be written as the electric field in the cross section, E of xy times e power minus j beta z. And you have a similar expression for the magnetic field intensity. And now, if we take these solutions and substitute them in the time harmonic electric field wave equation and simplify it, we basically get something of this form here, and you can work out the algebra here. We notice that this Laplacian, which was originally a Laplacian in x, y, and z, now becomes a Laplacian only in x and y, because the z component is now has basically become this beta square, and therefore you get this new equation, and this equation is called as the Helmholtz equation, which we will talk about. So also this omega square mu epsilon minus beta square is some complex number, which we can, it's some number which we can define to be equal to k square, which we will call as the dispersion relation. So this really defines the behavior of the, it basically denotes the mode, and we'll talk about the concept of a mode, but it basically talks about the behavior of a mode in frequency and beta. So if we define k squared to be omega square mu epsilon minus beta square, the previous equation just simplifies to, so this equation just simplifies to del xy square plus k square e is 0. And this is commonly called as the Helmholtz equation. And you have an analogous equation for the magnetic field intensity as well. These equations, if you notice now, these equations in E of xy now have, there is no dependence on z and there's no dependence on time, because those components have already been accounted for. Remember that the time component is just taken into account by adding a time harmonic e power j omega t, and the space component is just taken into account by adding a e power minus j beta z for a wave propagating in the plus z direction. And therefore, if you see these differential equations, they are only solved along the cross section of the waveguide, and they call as the Helmholtz equations. And if you notice these Helmholtz equations, these are also linear equations, and using the same trick we used before, since they are linear equations, we can use Fourier components or a Fourier expansion of E of xy in the cross section of the waveguide. So E of xy, for example, can be written as a sum of its Fourier components, where each one of the Fourier component is also a solution to the Helmholtz equation in the cross section. So E of xy can be written as a sum over some variables kx, ky of some vector valued constant, which is going to be a function of kx and ky, times the e power j kxx and e power j kyy, where these are basically the Fourier components. So these are oscillatory Fourier components along the x and y direction. To understand how the Fourier expansion takes this form, I would advise you to go read up more on things like a concept called two-dimensional and three-dimensional Fourier series or Fourier expansions. So now, if you substitute this form of the electric field, which is expanded as a Fourier series in the Helmholtz equation, what happens? So E of xy is now going to be this expression. And if you substitute this in the Helmholtz equations and then go through the solution, so I have gone through this step by step, you can have a look. And if you go through the solution, you basically end up with this kind of an expression, which is sum over kx, ky of k square minus of kx square plus ky square times c e power j kxx e power j kyy is 0. And what we basically need to do is we need to solve this equation to find the value of k. And once we find the value of k using this equation, we can then use the dispersion relation k square equals omega square mu epsilon minus beta square to find what is the effective epsilon of the cross section of the waveguide. So let me explain this further, what I mean by this. So from an intuitive perspective, what this equation actually is it's actually the energy conservation equation. And it's telling you that imagine you have some waveguide cross-section, and you have in that waveguide cross-section, you have some electric field, which is a function of xy, which must solve the Helmholtz equation. And because there are now in the cross-section, if you remember, there are several different regions of different epsilon with boundaries between them. If we get a suitable solution of E of xy that satisfies the Helmholtz equation as well as the boundary conditions in that cross section, then that would basically be equivalent to finding the values of C of kx, ky that create this E of xy that satisfies these conditions. Then using this equation, we can solve for what is the value of k square that satisfies this equation. And that k basically denotes an individual mode of the field in the waveguide. And from that individual mode, we can then use a dispersion relation to calculate what is the effective dielectric constant of that individual mode. And from this, you can calculate the effective index of that individual mode in the cross section. So thus the solutions to the Helmholtz equations, as I described earlier, is E of xy is written as some Fourier series, a Fourier expansion, and h of xy is also a Fourier expansion. So for the full solution, that is the Fourier solution, once you have these Fourier solutions along the cross section, the full solution x, y, z, t would just be the Fourier solution e power minus j beta c e power j omega t. So this would be the full solution to the Maxwell's equations in the waveguide for a single time harmonic frequency component omega and for a single kind of propagation constant beta. In order to find a general wave that's propagating through the waveguide, you just add over all possible betas and all possible omegas because you remember we are considering only the Fourier components. So the problem boils down to this. If you didn't understand what I meant earlier, because this is quite a complex idea and it requires some understanding of electromagnetic theory to get a feel for this. So what I'm basically saying is if we know what the C of kx, ky and the D's of kx, ky are, we have essentially solved the problem. And how do we determine the C of k? So why do we solve the problem if we know these? Because if we know the C's and we know the D's, then we can essentially get the solution to the electric field in the waveguide. And once we know the C's and D's, we can substitute in this expression to find out what is the K corresponding to that field distribution in the cross section, from which we can calculate the effective dielectric constant of the waveguide for that particular field distribution. So that is the kind of the step-by-step approach you do to solve the Helmholtz equation. So what exactly sets C and D? I already explained this. These are set by the boundary conditions in the cross section. So for example, imagine you had a metal and you already know that the solution of the electric field in the cross section is some Fourier expansion, but inside the metal, the electric field must be zero, and therefore you have some more kx, ky, c of this inside the metal region has to be zero. So there are certain constraints on what the C's have to be so that, for example, the electric field is zero inside metals and it satisfies certain normal and tangential boundary conditions at the dielectric interfaces. And that really sets certain unique values of C's and D's that solve the cross-section of the waveguide. And these unique set of C's and D's that solve the cross-section of the waveguide are called as modes. And we already know that we can calculate a K corresponding to the mode and an effective dielectric constant, epsilon effective, corresponding to that mode distribution. So that's what I've said here. So the boundary condition cross-section sets C and D. And once you know all the possible sets of C's and D's, which satisfy the boundary conditions, you find that you also find that only certain set of C's and D's satisfy all the boundary conditions in the cross-section. And it turns out that those C's and D's that satisfy the boundary conditions, which are called as the modes, have only certain possible values of K. That is, K becomes discretized. And therefore, the K is the number that denotes which mode you're talking about, and the K is discretized. And each K corresponds to its own epsilon effective, as we had discussed earlier from the dispersion relation. So now let's talk about the meaning of the mode. So a mode is basically a set of C's and D's that satisfies the Helmholtz equation in the cross-section. And this obviously has some pattern of the electric field in the cross-section called as a mode pattern, which is given by the E of xy and h of xy. And because we can use the energy equation that I described earlier for a given C and a given D to calculate K, K is basically only a certain set of Ks are possible corresponding to certain sets of C's and D's that satisfy the Helmholtz equation in the cross-section. And if you look at the dispersion relation I talked about earlier, you see it has a form that is hyperbolic in omega and K. So if you, omega and beta. And so if you plot beta versus omega, you get basically a bunch of hyperbolas where the intersection of the hyperbolas to the beta equals 0 is just K over square root of mu epsilon effective. And so imagine now you had different modes. So this is one mode, this is another mode, this is another mode, and so on. Each mode would basically correspond to some value of K that you can calculate, which corresponds to some C's and D's that satisfies the Helmholtz equation. And therefore, each mode will have this kind of a hyperbola. And each point here denotes a possible solution with a particular value of omega and a particular value of beta for a given mode pattern. And so you can see that there are multiple possible such mode patterns and they have a quantized K value. And so if you say had a certain frequency of excitation, so imagine your waveguide has a certain omega. So imagine the omega was lying here, then this omega would basically excite two modes in the waveguide because there are two possible mode patterns that satisfy the Helmholtz equation in the cross section. But if the frequency was lower, say it was here, then only one mode pattern is possible in the cross section. However, if the frequency is less than a certain than the lowest cutoff frequency, then you find that no mode pattern is possible in the cross section. That means no mode can satisfy the boundary conditions in the cross section, and therefore such a wave cannot be propagated inside the waveguide. So the waveguide is basically becomes frequency selective, and therefore depending on frequency, it can excite different modes. And if the frequency is less than a certain amount, it cannot excite any mode. So that is the meaning of that. And so if you look at what do these mode patterns look like, physically look like, if you were to solve the Helmholtz equation in different cross sections, and you look at how the E of xy and the H of xy are for different mode patterns. So here are some examples. So this is an example in a rectangular waveguide. That is basically a rectangle of metal, and inside you have a region of constant dielectric mu and epsilon. And you see these are the different mode patterns that are possible that correspond to different values of K that satisfy basically the Helmholtz equation in the cross section. Before going to this, similarly, you can have, these are the examples when you have a cylindrical waveguide. So imagine you had a fiber optic cable where this is basically the core of the fiber, and then outside there is a material of a lower dielectric constant, and these are the possible field patterns that you can have inside this waveguide. Similarly, you can have mode field patterns in a coplanar waveguide as well as a microstrip waveguide. So, as I mentioned, this is a good example of a typical, basically for the rectangular waveguide I showed here, this is a typical dispersion relation that you get. And you see that depending on frequency, there are different possible mode patterns that solve the Helmholtz equation in the cross section. So depending on frequency, you can basically excite different modes inside this waveguide cross section that propagate along the z direction. So now this also I explained earlier, and this pertains to signal integrity. So how does this dispersion relation pertain to signal integrity? So if you look at this curve, you can show mathematically that the slope, the inverse slope of this curve in the beta omega graph, which is omega by beta, is just the velocity that the wave has in the waveguide. So you can see how depending on the frequency, even for a single mode, the wave velocity actually changes. And if you go to each different mode has a different wave velocity in the waveguide. This is because each different mode will have a different mode field pattern in the waveguide cross section. And therefore, if you remember, it has a different value of K, and therefore it would have a different value of epsilon effective, which is calculated from the dispersion relation. So imagine now you had this transmission line, you had a waveguide that is connecting a transmitter and receiver, and say the transmitter side is actually sending a digital signal, which is a bunch of ones and zeros. This digital signal can be resolved, can be broken down into its frequency components, say there's some fundamental component and harmonics. Each one of these frequency components will now end up having a different mode field pattern and could excite different modes in the waveguide, and hence could have a different wave velocity as it propagates through the waveguide. And therefore, each one of these signals could arrive at a different time. So the higher frequency signals could be more delayed as compared to lower frequency signals and so on. And this leads to signal distortions and ultimately leads to bit errors and other signal quality issues. So this is how the concept of the mode and the mode field distribution in the cross-section of the waveguide is an important concept when it comes to signal integrity. So typically what people do is they design the waveguide in such a way so that over the frequency range of interest, only the fundamental mode or the lowest mode, for example, this mode would be excited in the waveguide. And irrespective of what higher order frequencies you have, the waveguide is designed in such a way that those higher order frequencies do not excite other modes or higher order modes in the waveguide. Because if they do excite these higher order modes, then these higher order modes basically cause signal distortions because of the different propagation velocity in the waveguide. Yeah. So now so till now we have basically yeah, 1 second. So till now we have basically talked about the waveguides and talked about the concept of how to solve the Maxwell's equations in the waveguide. But now let us go from the concept of a waveguide to the concept of a transmission line, right? So what is a transmission line? A transmission line is basically a one-dimensional waveguide. Now, in order to go from the waveguide into the transmission line approximation, the main consideration, that is the main concept, is that the wavelength. So imagine the highest, the shortest wavelength in your signal. If that shortest wavelength is, say, much smaller as compared to the length of the waveguide in the propagation direction, then you have to use telegraph equations along the propagation direction. However, if that wavelength, the highest wavelength, the lowest, shortest wavelength component, that wavelength is still much larger compared to the dimensions in the cross section of the waveguide, then you don't need to consider the distribution of field in the cross section, and you can basically just define voltages and currents in the cross section, and therefore you can go for a transmission line model. So that's why I've shown here. In case a waveguide is a transmission line, what we can do is for these electric and magnetic fields, we can compute the voltage, which is just simply integrating the electric field dot dr from one metal to the other. And the current will just be defined as the integral over a closed loop of h dot dl over mu. And now that we define these voltages and currents, we can represent the cross-sectional sections of the waveguide as a bunch of RLGC components, differential RLGC components, which are connected in cascade to describe the overall behavior of the entire waveguide. And then you can define something called as a characteristic impedance, which is just the ratio of the voltage to the current at any location within the waveguide. Yeah. And so now that we can define what is the voltage and what is the current based on these field parameters, when in a waveguide, which is basically a one-dimensional, sorry, in a transmission line, which is basically a one-dimensional waveguide, you can now go on to describe how to calculate the inductance and capacitance per unit length. So remember that the inductance is half Li squared, which is just going to be the integral of the magnetic field energy in the cross section, for example. And therefore, the inductance per unit length is defined this way. And similarly, you can have an expression that defines the capacitance per unit length, conductance per unit length, as well as the resistance per unit length. And you can put all these things together to basically generate the transmission line model. So now for a transmission line, so you can have either a microstrip transmission line where you have one conductor here of some width, which is present on the dielectric of some height, and bottom you have a ground plane. And so for this, you can solve basically the Helmholtz equation, get the field distribution. From the field distribution, you can calculate what is the inductance and capacitance per unit length. And from that, you can essentially obtain what is the characteristic impedance of this transmission line. And why the characteristic impedance is actually important will come later on when we talk about signal integrity. You can also calculate the epsilon effective by the methods I already described earlier. And similarly, you can also have other waveguides. For example, you can have an embedded microstrip. You can have a strip line, which is basically one metal in the center with a ground plane on top and bottom. You can also have a coplanar structure where you have the signal line in the center, and you can have two ground lines which are adjacent to it with some distance between it, like some gap between it. And here the field is basically confined between the signal line and the ground in plane, and this is called a coplanar waveguide. And similarly, these are some numerically determined expressions for the characteristic impedance and the effective index, effective dielectric constant. I think this I just included here just to give an idea of like when to use which kind of a waveguide. So here I basically plotted, and we haven't talked about this yet, but this is basically, think of it like the transmission, basically the transmission loss. So you would see that the transmission loss in a coplanar waveguide falls relatively slowly compared to the transmission loss in a microstrip. And you find that after some frequency, on the PCB, a coplanar waveguide becomes less lossy as compared to a microstrip waveguide. So depending on the kind of frequencies that you operate on and depending on technologies, you may have to design different kinds of waveguides to be used on your PCB. I do want to take these last few moments to talk a little bit about characteristic impedance because I don't think I explained this very well. So I think this concept is quite important, which is when do you go from a waveguide to a transmission line? So I just want to talk about this again. So remember, right? So when do you use a lumped element versus when do you use a transmission line? So if the length, so imagine you're considering a link of a certain length. If the length of the link is much smaller as compared to the wavelength of the signal that is being sent through the link, then there's not going to be much phase difference between one end of the link to the other end of the link, and therefore you can treat the entire link as a lumped element. However, if the wavelength is smaller than the length, then you have significant phase difference of the signal when you go across the length of the link. And therefore, in such a situation, you no longer can treat it as a lumped element, and you have to start using basically the transmission line model, where the entire link is divided into a bunch of differential elements, where each differential element has a differential resistance, inductance, conductance, and capacitance. Okay, so now we have talked about how to go from a lumped element model to a transmission line model. However, say you keep increasing the frequency even further, then what happens is the frequency becomes such that the wavelength of the signal becomes much, much smaller than the dimensions in the cross section itself. And when the wavelength of the signal is much smaller as compared to dimensions in the cross section of the waveguide, then you have phase differences in the cross section itself, and you no longer can define a voltage and current. In such a situation, you no longer can use the transmission line model, and you have to go for a full waveguide model by solving the full Maxwell's equation. That's why when you go into the photonics domain, the optical domain, you no longer can use characteristic impedance and RLGC parameters, and you have to go on to solve the full Helmholtz equation and describe the behavior of the waveguide in terms of its effective index, right? So within the transmission line model, that is, the wavelength is basically short enough that along the propagation direction, there's significant phase differences, so you have to use differential elements. But along the cross section, the wavelength is still long enough compared to the dimensions in the cross section that you can still define a voltage and current, right? And so once you can define this voltage and current in the transmission line model, then from the voltage and current, you can calculate the inductance per unit length and the capacitance per unit length, from which you can calculate the characteristic impedance, the effective dielectric constant, and so on. So this is the this is the overall view of how to go from Maxwell's equations to the concept of waveguides, and eventually to the concept of the transmission line model. So in the next lecture, we'll go more into details about the concept of signal integrity and talk about the various nuances and difficulties that occur when you're sending a signal across a link at broadband frequencies. Thank you.